Hi friends, let's see the velocity analysis. So we have a category of relative velocity method as well as instantaneous method. We have to see relative velocity method of two bodies moving in straight line. The application of vectors for relative velocity of two bodies moving along parallel lines and indicated lines. Consider two bodies A and B moving along parallel lines in the same direction with absolute velocities VA and VB such that VA less than VB. The relative velocity of A with respect to B is VAB is equal to vector difference of VA and VB, that is equal to VA bar minus VB bar. So the relative velocity of A with respect to B, that is VAB, may be written in the form of vector form VA bar is equal to OA minus OB, from which the relative velocity B with respect to A we can write as VBA is equal to vector difference VB and VA is equal to VB bar minus VA bar, that is AB is equal to OB minus OA. Now consider the body B moving in an inclined direction as shown. The relative velocity of A with respect to B may be obtained by law of parallelogram of velocities or triangle law of velocities. Take any fixed point O and draw vector OA to represent VA in magnitude and direction to some suitable scale. Similarly, draw vector OB to represent VB in magnitude and direction to the same scale. Then vector BA represents the relative velocity of A with respect to B. The similar way as discussed above, the relative velocity of A with respect to B. So VAB is equal to vector difference of VA and VB is equal to VA minus VB. So BA is equal to OA minus OB. That is A specified VA and B specified VB. The relative velocity of two bodies moving along inclined lines. Similarly, the velocity method of relative velocity of B with respect to A, VBA is equal to vector difference of VB and VA, that is equal to VB bar minus VA bar. So AB is equal to OB minus OA. Motion of a link. Consider 2 points A and B on a rigid link AB. Let one of the extremities B of the link move relative to A in a clockwise direction, since the distance A to B remains the same. Therefore, there can be no relative motion between A and B along the line AB. It is thus obvious that the relative motion of B with respect to A must be perpendicular to AB. Hence, velocity of any point on a link with respect to another point on the same link is always perpendicular to the line joining these points and the configuration of space diagram. So, velocity of a point on a link by relative velocity method. The relative velocity method is based upon the relative velocity of the various points of the link. Consider 2 points A and B as shown. Let the absolute velocity of the point A is known in magnitude and direction, and the absolute velocity of the point B is known in direction only. Then the velocity of B will be determined by drawing the velocity diagram. Take some convenient point O known as the pole. Through O, draw OA parallel and equal to VA to some suitable scale. Through A, draw line perpendicular to AB. This line will represent velocity of B with respect to A. Through O, draw line parallel to VB intersecting the line VBA at B. Measure OB, which gives the required velocity of point B to the scale. Notes one, the vector AB, which represents the velocity of V with respect to A, is known as velocity of image of the link AB. The absolute velocity of any point C on AB may be determined by dividing vector AB at C in the same ratio. C divides as AB. In other words, AC by AB is equal to AC by AB. Join AC is equal to the vectors OC represents the absolute velocity of point C, that is V suffix C, and the vector AC represents the velocity of C with respect to A, this VCA. The angular velocity of the link AB may be found by dividing the relative velocity of B with respect to A, this VBA, to the length of the link AB. Mathematically, angular velocity of the link AB, that is omega AB is equal to VBA divided by AB is equal to AB divided by small ab divided by capital AB. Rubbing velocity at pin. The links in a mechanism are mostly connected by means of pin joints. The rubbing velocity is defined as the algebraic sum between the angular velocity of the links which are connected by pin joints multiplied by radius of the pin. Consider two links OA and OB connected by pin joints O. Omega 1 angular velocity of the link OA or angular velocity of the point B with respect to O. Omega 2 angular velocity of the link OB or angular velocity of the point B with respect to O, and R is the radius of the pin. According to the definition, rubbing velocity at point O is equal to omega 1 minus omega 2, or the links move in same direction. Omega 1 plus omega 2 into R if the links move in the opposite direction. When the pin connects one sliding member and the other turning member, the angular velocity of the sliding member is 0. In such cases, the rubbing velocity at the pin joint omega into R. Omega is angular velocity of the turning member and R radius of the pin. Acceleration for a diagonal link. Consider 2 points A and B, rigid link, that the point B moves with respect to A with an angular velocity of omega radian per second and A radian per second square be the angular acceleration of the link AB. Acceleration of particle whose velocity changes both in magnitude and direction at p instant the following two components: the centripetal or radial component, which is perpendicular to the velocity of the particle at the given instant; the tangential component, which is parallel to velocity of the particle at the given instant. Thus, for a link AB, the velocity of point B with respect to A is perpendicular to the link AB. So, A or B is equal to omega square into length of the link AB. Angular velocity, the component of acceleration E, that is equal to omega square into AB is equal to B square BA divided by AB. The radial component of acceleration acts perpendicular to the velocity VBA. In other words, it acts parallel to the link AB. We know that the tangential component of the acceleration of the B with respect to ATBA, that is alpha into length of the link AB is equal to alpha into AB. Tangential component of acceleration acts parallel to the velocity VBA. In other words, it acts perpendicular to the link AB. In order to draw the acceleration diagram for link AB from any point B dash, draw vector B dash x parallel to BA. To represent the radial component of acceleration of B with respect to A, that is A or BA, from the point x draw vector is perpendicular to B J to represent the tangential component of the acceleration B with respect to A. Join B dash A dash. The vector B dash A dash known as acceleration image of the link AB represents the total acceleration of the point B with respect to A, that is alpha BA, and it is the vector sum of radial component and the tangential component of acceleration.